So just a quick introduction on support vector machine, SVM. So here even so this is also mainly a classification type of problem that we work here. So and here mainly it is somewhat similar to KNN, what we did in previous session. So here what happened is in KNN it decides on the basis of nearest neighbor. So on the voting of nearest neighbor, it makes a decision. Here in support vector machine, it takes a plane or a line on basis of which it tries to make a prediction that which class it should belong to. So let us try and so let us say here I have uh, a bunch of samples here. One is from another one kind of category, and there is this which is from another kind of category. So to make a distinction between them, I have put a line in between, and this line helps me to make a segregation between my two categories. So this is a typical type of classification problem that can be solved using support vector machine. And for most of the anomalies detection, I think SVM is mostly used. So it actually kinds of help you to segregate out one kind from the another, and it in returns help you to make a better classification. So this line, or what we call the vector that you see, that could be of any type. It could be a line, it could be a curvature like this, it could be a circle, or any other kind of uh, you know uh, a geometry that is that is possible. So there is no such restriction. You can change, or there are some parameters in R through which you can decide the curvature, which will decide the design of this vector. So let us understand few examples, and from there we will try to understand that which how it works. So here I have a scenario. Here I have stars and red circles, and on basis of this I want to make a distinction on basis of SVM. So here out of three planes that I have, A, B, and C. So can you tell me which plane will actually, or which line will make a better segregation between the two stars and red circles? B. Yes, it is correct. So there is no brainer at all, because A doesn't do a good job. It actually passes from one of the sample lines and also misclassifies most of my red balls. C does the same job as well, and but B is a very good option here available to me, because it puts both of them in a separate bucket or a separate space, and I have a clear distinction how I can decide that which category should belong to star and which category should belong to uh, red. So here one question is, so is it a kind of supervised learning or an unsupervised learning? So what can we say about SVM? Correct, it is a supervised learning. Reason being, so what happens here on the basis of this previous data, historical data, we create a plane on our data set, and on basis of that vector we try to classify the new out of bag samples that we get. So this is mainly the working of SVM, and it's a supervised in nature. So here let us take one more example and try to understand. So here I have this case. Here I have stars, and here I have red balls, and all of them are put into a separate category by using all the three planes. So B, C, and A, all of them works quite well. So here, which one should I choose out of these three? Out of B, C, and A, and why C? Correct. In that case, when I have created a already created a plane, and both and all those planes are making a correct classification in all the three cases, then my algorithm or the code that I have written, that will search for the maximum margin. So in this case, the maximum margin is with C. So C will be a better uh, vector in this case. Now let us take one more. So any questions here? Okay. Okay. So let us now take one more example. So here I have uh, both of them. So let's say I have this B and A. So which one will be better? Why B? So some of you have mentioned B. So see what happens with B, it makes a misclassification. One sample goes to another plane or another part of the coordinate. But in A, all of them are classified good. All of them are put into this different categories. So every thing on the left side of A will be star and right side will be red balls. So here what happens is, in case of margin optimization and misclassification, my first priority will be to avoid misclassification. So in B, I am getting a misclassification, and that is a higher cost. But in A, there is no misclassification, though it could be possible that the kind of margin that I am getting here is quite high in B compared to A. But still, more preference will be given to avoid any misclassification. Okay, so let us move to one other example. So here now I have something like this. This is my situation when one star is in between these red balls. So here I cannot draw a straight line. Okay, in this case what happens is my SVM will treat this star as an outlier. So because I don't have any optimized line to choose this or to segregate this red balls, because it is somewhere in between. So what will happen is it will classify this as an outlier and it will make the most optimized. So in that case, my straight line will be my vector here. Okay. So now here I have another scenario. Here now, so it is something like this. All the red balls are towards the origin, and it is surrounded by all the stars. So how will my vector look like? So here what I can do is I can make a spherical vector. So this is a good example of a spherical vector. What we were dealing with till now was only about I would say a linear one, or maybe a line, or mainly a plane. So here I have a case of circular, or if you add some more dimensions to it, it might become a spherical as well. So this is a good example that how it will treat this data. So here what will happen is, in this case, it will add one variable z. So z will be equal to x square plus y square. And now if I plot my z with x, it will be something like this. So all the x are here and y, and now I can draw a plane. I can create a plane here, and this will segregate easily. But z is completely a different variable that does not exist here. So what it will do is it will again transform it to its original format and try to draw a line in between like this. So this is how it works. A simple explanation of SVM. So any questions and any doubt till here? Yeah, it can be multi-labeled. I have explained only on the basis of two, just to explain you. Now the dataset that I will be working with, there I have taken three labels. So let us try to understand there and how it works in cases of multi-labeled data. So here we will be working with the iris dataset, and the same package that we used for naive Bayes, we will be using that. So head of iris dataset, let us attach and work with this. So here I have created a model for SVM using all my X or all my numeric variables that I had, and it will make a classification here on species on the basis of vector. So here, if I don't make a visualization, it will become a bit of a problem to understand that how it is working or how it is. So let us go through some of the text and or some of the prediction that how good it has been able to classify, and then we will look at the plot. So here if you can see, there are only two misclassifications here and two misclassification here. Apart from that, four misclassification, and all of them has been classified very well. So a good way to make this prediction. Okay. So kernel is mainly, so let me explain this. And so kernel is mainly the type of curvature that you're trying to explain, or the curvature which will help you to identify your vector. So here if I look at the kernel, so kernel here are mainly a linear, whether that line will be a linear, well, a polynomial or a radial base. So radial base could be parabola or a hyperbola, elliptical or a circular, a sigmoid. So these are the kind of kernel that are available with me. So you can change this, and you can check that which one suits you better. For example, here I have not specified anything. So it will takes its own assumption, and on basis of that, it tries to make a prediction that which one will suit better. So which one will work better, KNN or SVM? So that is again depending upon the entirely the algorithm that you have. So for example, if let's say the overall accuracy that I'm getting. Uh, so if that is good for KNN, then I will try to stick with KNN. Or suppose if I try to segregate a segment or try to predict a particular category, and if that category makes more sense to me compared to other categories, and that is my major priority, and KNN is able to predict that category more efficiently compared to SVM, then my priority will be KNN over SVM. And so which algorithm will work better, that is quite difficult to understand or quite difficult to explain. Only when you get hands on with that algorithm and try to implement, then depending upon the situation, it might work better or not. But which one will work better, that completely depends upon the situation. Accuracy is one measure, yeah, but in some cases, accuracy, even it is not same. What you are likely to say is that you don't generate much of false positive, and also you want to see, you want to classify your true positive more than your true negative. So that if in that case, if that becomes your priority, then accuracy is not the priority anymore. If true positive rather than the entire accuracy is what you're checking for, then you need to see differently. And in that case, a few algorithms might work differently. And like I did a case study previously, I have made a separate case study where a logistic regression, decision tree, and random forest all were compared together. And on basis of the comparison, what I found that logistic regression was most doable with out-of-bag data set, out-of-bag sample. And then I tried to make prediction on the basis of logistic regression. So that is where you need to work a bit and try to understand. So here, let's see if I am working with the polynomial type of kernel. So in the polynomial nature, let's see if it is something like this. It is for x square. So it is a kind of parabola, and now it is more flexible, if I can see. So let's say, if not like this, then a parabola is something, it is defined like this, and all my samples are here, and rest of my samples are somewhere like this. So here in this case, parabola works better. A linear line might not fit, because if I try to make a linear line, it might be a kind of misclassification. So linear might not fit here. Radial basis is somewhat like, let's say, so radial is mainly I have my origin, and on the basis of origin, let's say here I have an elliptical type of some structure or a circular type of some structure, something like this. Or I can have somewhat like a asymptotic type of structure. So these are mainly features of kernel that I have. These all I can make some changes using kernel. So there are some features available here in SVM tune. So I can make that tuning, and I can try to work with various types of kernel and see which one will work better. So let us try to see and try to understand. So here now my what I'm trying to do is I'm trying to tune my SVM. So here I have written the statement of tune. So I have saved my model here in SVM. Sorry, it is so it is just an SVM, and here I have mentioned that ranges of cost function and gamma function will range from so and so. So this will be a combination of three, and here cost function ranges from so and so. So it will give me the optimum value. So at which value my cost and gamma function will be optimum, and using this where I can select. So here if you mention, here if you see, I have not mentioned anything. It has made a just an assumption. The default value has been taken. But here now I am trying to impart, or mainly I am trying to throw many numbers at the same time and trying to come up with which one does the better job. So here I have for best parameters, cost function will be 1 and gamma zero point 0.5. So let us try to work with this, and k-fold cross validation, if you all remember that we have done with this, that what k-fold cross validation does, it divides the dataset into 10 and treats one as for test and another for train. Like this, it creates 10, and out of that, the best that comes out, it treats as final. So after that tuning has been done, let us try to tune our parameters to cost equal to 1 and gamma zero point 0.5, and now let us try to work with it and let's see how good it works. So here also if I see the prediction hasn't been so any changes in that. Same two misclassification I can see, two here and two here, so total four misclassification. So this is what we have achieved. So tuning that did not do much good to us, but yeah, in some cases when we try to make some good classification, then at that cases tuning is a good option. And also, as I have mentioned earlier, k-fold cross validation is a good option to minimize your error. So when you have a big data set and you try to minimize your out of back sample, k-fold will actually ensure you that it doesn't happen. So one last thing on this, that how can we visualize our support vector machine? So here what I have done is I have made scale of all the, so if I show you here, so here I have four numeric variables, length, width, and petal length and width. So here I have put them under the same scale. I have ignored species one and considering all these variables, putting them into a common scale, and then color is as integer. So color will be on basis of the species that I have. And here I have taken one of the parameter of SVM model, that is index. So index, what it does is it points us out those indexes of that data set which are closer to SVM boundary. So here if I run this SVM index, so my sample number 14, 15, 16, 19, these are type of boundaries to the SVM vector that I've created. So these are all my boundaries. So here what I'm trying to do is all my inner samples or the sample which is within the boundary will be denoted as 0, and one which is outside the boundary will be denoted as plus, or which is actually at the boundary, just at the boundary will be denoted as plus. So here I have spotted all the index. Now let me do one thing. So let me see if this is there or not. So if I run this, this is giving me that from 1 to 50, 1 to 150, if these things are there in there. So first in 150, it is not there in my index. So if you consider that first is not there, second is not there, what is there is 14, 15, 16. So this is 13, this is 14. So 14 is true. 14 is there, 15 is there, 16 is there, and then 19 is there. So for all of them which is there, it has mentioned as true, and which are not there in the indexes, they are mentioned as false. Now what I will try to do is for all of them which has been mentioned as false, I will try to denote it with 0, and for all of them which has been denoted as true, I will try to uh, visualize that as plus in my chart. So here what I have done is I have made it like this. So if I do a mathematical operation like addition or subtraction on true and false, it will treat false as 0 and true as 1. So here that has happened. So false plus 1 is equal to 1, and as true is equal to 1, so 1 plus 1 will be 2. So wherever there was true, it has been replaced by 2, and wherever there was a false, it has been replaced by 1. And now I want to plot this. So here I have my structure. So here, as you can see, these are the plus signs. So these are mainly the boundary of SVM, mainly the boundary, and these are the inner values. Again, here the plus sign, these are the mainly boundaries of SVM, and zeros are the inner values of for this as well. Here I have plus as the boundaries, and zeros are the values that are within the boundaries of SVM. So hope it makes sense. So any questions or in doubt, let me know.